Okay, so I'm going to tell you a little bit about big data sets and numerical simulations of particle physics. Okay, the underlying basic force in describing how quarks and gluons interact to produce nuclear physics is quantum field theory. And some things you might want to say is how do you compute the mass of the proton from the properties of the quarks and the gluons? And to do this, probably need to use quantum field theory. Also, it's found the same techniques we use in QCD for quantum chromatics theory of nuclear physics. The non-perturbative field theory is also used for theories for people trying to explain the Higgs boson from more fundamental theories. Okay, if you're interested in quantities such as masses, you have to introduce space-time lattice. And it's in four-dimensional space-time, three space and one time. And equations are put on the computer in a kind of clever way to respect various symmetries. Okay, so what happens in the lattice QCD calculation? You start off with a fixed volume, and lattice spacing essentially use the Monte Carlo methods. So you introduce some random numbers, and then there's different random numbers. You get different samples of the thing you're attempting to estimate. The most fundamental objects are gauge configurations. They're essentially snapshots of the vacuum. On top of those, we then generate propagators to describe the evolution of basic particles, such as the quarks. Then you tie together propagators to form correlators. And these start to describe the properties of observed particles such as the proton. And then from the correlator, you do a statistical analysis to obtain, say, the mass of the proton. And this is the number that's published. And all these things have different data sets. You have a bunch of copies of these things, so the gauge configurations. Propagators tend to be a bit bigger than the gauge configurations. Correlators are smaller. But this calculation repeated, obviously, there's no physical lattice. It's just a kind of an artifact for solving the equations. So you have to repeat the calculation. Lattices, different sizes, different volumes, different masses. I need to keep track of all the lattice parameters, even the algorithms used to do it. And there are various numbers of different ways of putting the equations on the lattice. And from the continuum, you have to keep track of all this stuff. Okay, here's some typical lattice sizes. So at the Cambridge cluster, this big cluster in the UK, the HPC collaboration, which I remember has stored an allocation of 400 terabytes. So the data is, these are sort of lattice units. But a single file, one part of the Monte Carlo process, is a size 14 gigabytes. And at Cambridge, I just counted, there's 184 of them to give you 2,500 gigabytes roughly. For smaller lattices, this is part of the analysis. This is actually also coarser lattice spacing. The files are 4.3 gigabytes. This is an individual snapshot of the vacuum, and there's 1,000 of them. And that's obviously around 4,400 gigabytes. A typical paper by the HPC collaboration uses the order of 10 ensembles. There's also intermediate data sets that are calculated and sometimes deleted, but could be reused if you had more storage available. And this is part of a bigger data set. The actual configuration is generated in the US by something called the Mill Collaboration. They keep a library of much more extensive ensembles, lattices. So I told you before, all this data comes tagged with stuff, and one way to do it, you have to include all the parameters. One way is to include a text information included with a binary file at the beginning. You have a couple of records saying what the lattice volume is, or sometimes the metadata is included as a separate text file. Sometimes this metadata is coded up as XML, but more often not, it's used as a text-based system. And then when we process it, we will hack around with the Perl or Python or Bash. We need to process some of this information. There was some work on international standard file formats, and it took like 2 years to argue over an XML schema for the gauge configurations. And I've been playing around using things like NetCDF, which is a bit more self-describing data sets rather than just this system up above. Computers we use in the UK, we also have international resources as well. Come from Dirac, distributed research using advanced computing, and this is provided by SDFC. Actually, the money comes from the government. That's for HBAC-based research in particle physics, astronomy, and cosmology. The people who do like engineers have a separate machine up in Edinburgh. At Plymouth, we use the Cambridge cluster, which has 9,600 cores, and the Edinburgh Blue Gene Q. This is an older machine now, which is getting close to final retirement. And this has around 6,000 nodes. Funding-wise, the Dirac 1 was in 2009. There's about 12 million. Dirac 2 came around in 2013, another 15 million. So it funds, there's a couple of other machines distributed around the UK, which is funded by this Dirac collaboration. We're waiting for funding for Dirac 3. It's not clear when that's going to come. Obviously, the government's thinking about other things at the moment. But it looks as though we may get funds for Dirac 2.5 this year, which would be a kind of modest refresh of some of these machines. In the past, funds were more distributed around the UK, so in this Dirac 1, we got part of the Plymouth cluster. Now, when you apply for time on these machines, somehow this is built in, so we get some kind of benefit from just applying for computer time at Cambridge or Edinburgh, one of these places. So I told you it's kind of important that you have all these data sets all spread out around, and in the past, in some collaborations, they're actually the calculations spread over different superunit sites. In the early 2000s, there's this idea of a computational grid, and people put a lot of work into building a data grid for lattice QCD based on Globus. So the UK QCD grid ran from 2002 to around 2011, 100 terabytes stored across 8 sites, one of which was in the US. There was an international body formed of all different lattice QCD groups that worked on standards and also tried to get an international grid that would talk to each other. And this all sort of worked together. There's still grids in use in Japan and continental Europe, that just the funding dried up. So this is a brief picture of how the thing worked. These storage elements would store data, say at Glasgow or Liverpool or Southampton. And then there was a central node at Edinburgh with a metadata catalogue. And if you're a little client and you want to get some data set, you put in the logical name and it translates to a physical name, and you get your gauging verification, and things were replicated. But the funding dried up for that, and there was no longer anyone around to maintain it or build hardware. Okay, so what kind of software are there? Various open source codes to generate these correlators and gauging configurations, typically written in C++ or C, a few still written in Fortran, and a couple in the US I see people now using this LUA, which is a fast scripting language similar to Python, but with much better performance. All the codes run on big parallel machines. A good lattice QCD code should have efficiency of around 20%. There's various people who just spend all their time tuning these little machines, tuning these codes to get good efficiency. Important the Monte Carlo process, where the physics come from is statistical analysis when you combine all these different correlators, and these are typically written in C, R, MATLAB, C++, and they're all called external libraries to do chi-squared minimization and metric conversion. They tend not to be open source. There are a few open source, but they also tend to be a bit of a mess because you always want to mess around a bit with the statistics. It's hard to keep out. One of the problems with some of these codes, there tends to be very skimpy documentation. So if you say to documentation to one of the developers, they say, oh yeah, sure, just read the source code. The Department of Energy in the US funded a big software effort called via SIDAC, resulting in a bunch of open source codes like Milk and Chroma. These ones do some of these things at the top, generate correlation configurations, and they're also libraries on specialized machines. People sometimes build a specialized machine for lattice QCD. They don't want to install the standard MPI library, message patching interface, because lattice QCD codes don't use all of it. So they try to write a different new lattice message patching library that uses a subset of the communications that's used typically by lattice QCD codes. Okay, and this is a kind of continuing effort, and the money's distributed around labs and universities. Okay, so we don't really do that much visualization in lattice QCD. Obviously, scientists will mostly do XY graphs to say the proton mass as a function of lattice spacing or volume. This is a plot sometimes you'll see. This is a 3D slice of 4-dimensional space-time. This is actually action and the different colors, different values. The slide problem, the number of problems with this, say, it's not clear how to connect this to, say, the mass of the proton. There's also depends on the procedure to generate it. So they're kind of pretty, we're still not effectively using these things to do qualitative physics. Okay, obviously computers are getting bigger, so obviously our data sets are getting bigger. We're also doing more physics, including electromagnetism and isospin breaking, and this means more data sets, more parameters to keep track of. There are also newer algorithms that generate more data that can be reused, will help further increase. So we still need better tools for tagging, reformatting, and moving data generated by supercomputers. So hopefully the tools developed by big data will help us, or better still, we use our experience in working with big simulation data sets to help other big data projects outside our speciality. Okay, that's what I wanted to say. Thank you.